So, last time we saw the definition of what a Dedekind domain is, and I left it as an exercise to prove that a principal ideal domain is a Dedekind domain. We defined the notion of fractional ideal in a Dedekind domain, and notice that product of two fractional ideals is again a fractional ideal. Our main theorem today is to prove that the set of non-zero fractional ideals in a Dedekind domain forms a group under multiplication. So, to that end we proved last time that if you have a non-zero prime ideal, then it has an inverse. Okay. So, let us continue the study of Dedekind domain, the algebraic properties of Dedekind domain. So, today we are going to prove the following proposition first. Let R be a Dedekind domain, and I will write DD for small, that I did last time as well, Dedekind for short for Dedekind domain. So, let R be a Dedekind domain, let A be a non-zero fractional ideal, a non-zero ideal in A in R, non-zero ideal in R, then A has an inverse, okay, which means that there exists a fractional ideal B such that A times B is equal to R. So, we proved this proposition last time for prime ideals. Now, if this proposition is not true, what we can do is we can take let S be the set of all non-zero ideals of R that do not have an inverse. Okay. So, we want to prove that S is empty. S is the empty set, right. So, let us assume to the contrary, assume S is not empty. We used this argument last time as well, because R is a Noetherian ring, any non-empty subset of ideals of R will have a maximal element with respect to inclusion. So, as R is Noetherian, S has a maximal element say A, okay. And we want to get a contradiction from this, right. Our assumption is that S is non-empty. If we get a contradiction, then our assumption must be incorrect, right. All right. So, what do we know? Well, we know that A is not equal to R, right, because R is invertible. We know that A is not a prime, because we proved that prime ideals, non-zero prime ideals have an inverse, but A is a proper ideal of R, as A is contained in R but not equal to R. There exists a prime ideal P such that A is contained in P. Okay. So, what we do is we know that P has inverse. So, we look at P inverse and we know that this contains R, right, from previous proposition. Okay. This means that if I look at A P inverse, then this contains A, okay, and because A is contained in P, this means that this is contained in R. Okay. So, A P inverse is an ideal. Now, there are two cases. Okay. So, case 1 is that A P inverse is equal to A, but we can prove that this case cannot occur. Okay. And how do we do this? We use the same strategy that we did in the proposition where we proved that prime ideals have inverse. Okay. So, let beta be an element in P inverse, but not in R, then beta times A is contained in A, right, because of this, because we are in case 1, and we will get a contradiction from that. How do we do that? Well, let A1 up to AN be generators. So, I am repeating the same argument as before, but it is good to see this argument again. Generators of A as R module as an ideal, okay. Then beta times AI is summation Bij Aj j going from 1 to n. Okay. So, this is where we use that beta times AI is also contained in A. So, if you let B be the matrix Bij and f of t to be determinant of t times identity minus B, this is a monic polynomial in R, right, and we know that f of beta is equal to 0, which means beta is integral over R, but R is integrally closed in K, hence beta is in R. This is a contradiction, but you see this is a contradiction to the latest assumption we made. We have made two assumptions. Our first assumption is that S is non-empty, and our second assumption is that A P inverse is equal to A. So, this only contradicts the latter one, and so hence A, sorry, not this A, the script A, P inverse is not equal to A. So, this means that we should be in case 2, which is that A P inverse, it of course contains A, but is not equal to A. Okay. So, it is not equal to A. So, if A P inverse is not A, then A P inverse does not belong to S, as A is a maximal element in S. What does this mean? This means that A P inverse has an inverse, hence there exists B, a fractional ideal such that A P inverse times B is equal to R, but this means that A P inverse B is equal to R, which means that P inverse B is inverse of A, a contradiction, right, again, because we assume that A has no inverse, right. Hence, S is empty and we are done, right. So, that is the proof of this proposition, that every non-zero integral ideal in R has an inverse, right. Now, you can guess what the next statement would be. So, we proved that every non-zero prime ideal has an inverse, then we proved that every non-zero integral ideal has an inverse. So, next proposition would of course be that every non-zero fractional ideal has an inverse. Every non-zero fractional ideal of a Dedekind domain R has an inverse. Okay, and how does one prove this? Well, we know what all the fractional ideals look like. You can multiply a fractional ideal by an element in the a non-zero element in the field of fractions and get an integral ideal. So, let A be a non-zero fractional ideal of R, then there exists x which is in R but not 0, such that x times A is an ideal in R, right. That was the first thing we proved about fractional ideals. Okay. By the previous proposition, x A has inverse, say B. Okay. So, x A times B is equal to R, right, which means that inverse of A is x times B, which is again a fractional ideal, right. So, if you multiply fractional ideal by a non-zero constant, you again get a non-zero fractional ideal. Okay. So, that is what we wanted to prove, that every non-zero fractional ideal has an inverse. So, now we have proved our main theorem. Let R be a Dedekind domain the set of non-zero fractional ideals of R denoted as IR forms a group under multiplication. Okay. And so, proof. So, we take two fractional ideals, right. First of all, A times B, which I will recall, this is summation AI BI, I going from 1 to n, such that AI is in A and BI is in B for 1 less than or equal to I less than or equal to n, is a fractional ideal. So, we saw this last time, that product of two fractional ideals is a fractional ideal, and if A and B are non-zero, A times B is also non-zero, right. So, this A times B is in IR. So, we have a binary operation on IR which is given by product of fractional ideals, and this product has identity. So, R is identity, right. So, A times R is equal to A for all A in IR, right, and then associativity and commutativity is fine. So, associativity and commutativity is easy. So, I am not going to say anything about that, and we proved that existence of inverse. Okay. And so, we are done, right. So, our major theorem was split in three parts. First, we proved that every non-zero prime ideal has an inverse, then we proved that every non-zero integral ideal has an inverse, and then we proved that every non-zero fractional ideal has an inverse. So, that is the that was the main point. Everything else about being a group is easy to do. Okay. All right. So, Once we have this, we can actually prove a substitute of fundamental theorem of arithmetic. So, let me write that here. Okay. So, first let me give you an exercise. Let R be a Dedekind domain and A1 and A2 be two ideals in R. Then the following 4 statements are equivalent. And what are the 4 statements? Well, A1 is contained in A2. This is same as saying that A1 A2 inverse is contained in R, which is same as saying A1 inverse A2 contains R, and this is same as saying that A2 divides A1. So, what does divisibility of ideals mean? It is exactly like what you have for integers. This means there exists an ideal B such that integral ideal B such that A2 times B is equal to A1. Okay, so that is what divisibility means. So, I think this is a good exercise for you to do to understand how the multiplication in the set of ideals for Dedekind domain works. So, here is a nice theorem which says that, so again let R be a Dedekind domain any non-zero ideal in R, non-zero integral, so whenever I say ideal I mean integral ideal, any non-zero ideal in R can be written as a product of prime ideals in a unique way up to reordering. Okay. And so, here is a remark about this. So, this theorem is an analog of the following thing that we learn in high school. So, any integer, so this is called fundamental theorem of arithmetic. What does it say? Any integer n bigger than 1 is a product of prime numbers in a unique way. Okay. And we saw that this, the analog of this over in number rings fails, right. In OK where k is a number field, it fails in general. So, the substitute for it is that rather than looking at factorization of elements in a number ring, you look at factorization of non-zero ideals. And the proof is also similar to what you would do for fundamental theorem of arithmetic. Okay. I will tell you in what way. Let us look at the proof. So, I want to show that every non-zero integral ideal is a product of prime ideals. So, what I do is I look at the set of all non-zero integral ideals that cannot be written as product of primes. Okay. So, this is a common way of proving things for Noetherian rings. Okay. So, let S be the set of ideals of R that cannot be written, set of non-zero ideals that cannot be written as a product of prime ideals. Okay. And again we want to show that S is empty, right. And so we are going to assume that S is non-empty, and then we will try to get a contradiction from that. Okay. What do we do to prove fundamental theorem of arithmetic? Well, we use induction on the set of natural numbers bigger than 1. Okay. So, 2 is a prime, 3 is a prime, 4 is 2 into 2, and so on. So, we say that let us assume the statement is true up to for all integers up to n, and then we take n plus 1, and if n plus 1 is a prime, then we are done. If not, it is a product of two integers, both of which are less than or equal to n, right. And then we know that each of those integers is a product of primes, right, and that is how you get prime factorization of n. In a general Noetherian ring, this is the argument that substitutes induction, right, because you prove that any non-empty set of ideals has a maximal element using the ascending chain condition, which is what replaces induction. Okay. So, if S is not empty, then it has a maximal element say A, right. And now we know that A cannot be R, because R is empty product of prime ideals, and we know that A cannot itself be a prime, because prime ideal is a product of prime ideals, right, P is equal to P. So, so there exists a prime ideal P such that A is contained in P, right, and again we do the following. So, A is contained in P inverse A, which is contained in R, right. So, as in the first proposition we proved, if the first inclusion is an equality, then we want to get a contradiction. So, if A is equal to AP inverse, then of course, we can use the argument that we did in the first proposition, but we do not need to do that anymore, because we know that A has inverse. Then R is equal to P inverse, hence P is equal to R, right. This is a contradiction. Therefore, A is contained in but not equal to AP inverse, right. Okay. So, this means AP inverse is not in S, right. Again I am repeating the same argument again and again, because it is useful to do so, right. So, to see the same argument again to understand it really well. So, this means that AP inverse is a product of primes, prime ideals, right, prime ideals. Okay. So, there exist prime ideals P1 up to Pm such that AP inverse is P1 up to Pm, but this means that A is also a product of prime ideals. This is a contradiction, and hence S is empty, right, and we are done. Okay. So, every non-zero ideal is a product of prime ideals, right. So, in particular, if X is an element of R minus 0, so I do not want the 0 ideal, because I proved that every non-zero ideal is, oh sorry, this does not quite finish the proof, I am sorry, this just proves existence of okay. So, this proves existence of prime factorization. Now, we want to prove uniqueness, right, up to reordering. So, let us say A is P1 up to Pm and it is also equal to Q1 up to Qn, right. And again I am going to use the same strategy that one does for fundamental theorem of arithmetic. So, it is good to know the proof of prime factorization over integers. Okay. So, what does this mean? This means that so, I want to show that m is equal to n and then Pi is equal to Qi up to reordering, right. So, Pi is equal to Qi for all I. Anyway, so this means that P1 contains Q1 up to Qm, and we used this argument last time that this means that one of the Qi's is contained in P1. Okay, so, if Qi is not contained in P1 for all I, then we take Xi in Qi but not in P1, and you look at x1 up to xm, this is in P1, but none of the xi's are in P1. So, this contradicts that P1 is a prime ideal. Contradiction, right. Hence, there exists I such that Qi is contained in P1. Okay. And so, after rearranging, we may assume that Q1 is contained in P1, but they are both non-zero prime ideals, hence they are maximal ideals. Hence they are equal, right. So, Q1 is equal to P1, and so we get Q2 up to Qn is equal to P2 up to Pm, and now we can keep going, right. Use induction on m and n, right. So, I am not going to give the details of this induction process, it is an elementary induction. Okay. All right. So, we have proved that any non-zero prime ideal, any non-zero ideal in a Dedekind domain is a product of prime ideals. Okay. So, I gave you this example, let us revisit that. When k is q square root of minus 5 and OK is z square root of minus 5, and in this I told you that 6 has two distinct factorizations into irreducible elements. Right. But what happens if you take the ideal generated by 6? Okay. So, what happens in this case is you can write it as I mean these two ideals are the same, but let me not get into that thing. Okay. And each of this is a prime ideal. Factorization of 6 OK. So, 6 OK is an ideal, and this is how you get a prime ideal factorization of this ideal. None of these ideals are a principal. So, you cannot generate them by one element, and that is the whole reason why factorization into irreducible element fails, but factorization into prime ideals holds. Okay. So, today we have proved that any non-zero ideal in a Dedekind domain is a product of prime ideals, and that factorization into product of prime ideals is unique up to reordering. So, this becomes our substitute of fundamental theorem of arithmetic, and next time we will continue to study general properties of Dedekind domain, and then we will prove that the ring of integers in a number field is a Dedekind domain, and we will resume our study of rings of integers in a number field.